Hi everyone, my name is Chen. I'm from BioMS. In this video, I would like to introduce you about xcmsViewer. It is a platform for you to explore the untargeted LC-MS-MS-based metabolomics data. So the idea of xcmsViewer is to link advanced statistical analysis results with the raw mass spectrometry data, so you can work with the data interactively and evaluating both the statistical results and the quality of mass spectrometry results together. Yeah. So before this you have to be familiar with a few concepts, like what is a chromatogram, what is a mass spectrum, and how we can use it for identifying a metabolite. If you are not familiar with this concept, you can refer to the link below the video, and there are many nice videos to introduce them. We won't talk them more. So in this video, I will use example data to demonstrate how we can use xcmsViewer in our data exploration. First, we look at how this work or how this study was designed. So this is a study tried to understand how metabolites change after the durative exercise. And we also know that after durative exercise, the troponin 1 level will increase, which may relate it to the heart failure or kidney disease or sepsis. And we also want to see which metabolite may relate to the troponin 1 level changes. So in this experimental design, we collected blood samples in 3 different time points. That is before a marathon, and immediately after the marathon, and 24 hours after a marathon. So during that day, the candidate took a rest. So at every time point, we collected 4 samples. So in total, we have 12 samples. And also the troponin 1 level was determined in these samples already. So in this experiment, we generated and targeted metabolite profiling using LC-MS-MS-based metabolomics method. So to answer our biological question, we performed 3 statistical analyses. The first one is Pca. It's mainly for the purpose of quality control. And we also performed the t-test to compare the samples collected at different points. So we have 3 groups. So we performed the 3 pair t-test. And also the last thing we done is to correlate the metabolites we measured with the troponin 1 concentration. So all these results are pre-calculated and stored in an object that can be visualized using the xcmsViewer. And now let's go to the xcmsViewer. So when you log into the xcmsViewer, you open xcmsViewer, so you will see such an interface. The first thing you need to do is to load the data set you want. So usually for one sample, we measure it on both positive or negative mode. And because different metabolite may be measured at different mode, for example, maybe amino acids are more likely to be detected or better detected in the negative mode, but some other compounds may better detect in the positive mode. So as an example, we look at the negative mode here. So the layout of xcmsViewer is half left and half right. So on the left side, we see the information about samples or the information about the features we detected, and also we can visualize them using different ways. So the first thing you may want to check is the sample table. Here, the table lists all the samples measured in this experiment. And we can see the labels of the 12 samples and which group a sample belongs to. We have 3 groups after, that means immediately after the exercise, and 24 hours after the exercise, and also before the exercise. And the third column here is the troponin 1 level. And the fourth column is the file name. So in this case, it's just the same as label. Also, actually, this is just a toy example only for the purpose of demonstrating the use of xcmsViewer. So you shouldn't derive any biological knowledge from this example. And then the next thing we want to do in our data analysis, maybe to check the Pca result, to see if the samples from different groups separated in our Pca or PC1 or PC2. So this can be done by looking at the sample here. By default, if we have Pca performed, the x-axis and y-axis are always PC1, PC2. So what you need to do is to color the sample using different variables. For example, if we want to know if the information about the group, here you can see the samples from different groups are separated by different colors. And here in the middle is the 24 hours after the exercise. On the left side, it is immediately after the exercise. And the far right side here is the before exercise. I think then we can say PC1 separating the 3 time points is a good thing. Immediately after the exercise is most different with the before exercise. And the metabolomic profiling goes more similar to the before after 24 hours of rest. Yeah, that's a good thing already. So one other thing you can do is to, when you mouse over a pond, you can see some information, and you can add more information to the tooltips here by adding columns here, for example, label. Now the label information is also in the tooltips. Yeah. And so you can also do some analysis by selecting a subset of samples already. So this can be done by either the box selection or a lasso selection. So if we use box selection, we can select the 4 samples on the right side. Now we can go to the sample general here. The sample general lists the samples we selected. And of course, in this case, we know they all from the time points before exercise. Yeah. And now if we want to ask the question, if we want to interpret for example, if we don't know what may correlate with PC1, what you may want to check is if the sample we selected here have a high level of troponin 1. This can be done by looking at by selecting variables. On the top right corner here, we can select troponin 1 level. So basically we split our samples into 2 groups, the selected one and the unselected one. And each point here is a sample, and the y-axis now is the troponin 1 level we just selected here. And we can see here the selected samples don't have a high or low, don't have significantly high or low troponin 1 level. We can also select some other samples, for example, on PC2, also no significant result. But if we select here, we can see the 4 points on the left side have high troponin 1 level. So this is one way how you can interpret the Pca result or any other result visualized on the left side. You can also correlate the selected samples with some categorical variables. For example, As an example, we can select the group here. Of course, we know that we are selecting those 4 samples after exercise. But you can select any variables you have here, yeah, in your application. And now we can see there are 3 tables. On the top is contingency table. Every row here, the row here tells you the selected or unselected sample, and the samples are according to the group variable have 3 groups after 24 hours and before. And then the table in the middle shows the fold change of the contingency table. That means we observed such a number, how much it is higher or lower than the expected value. And the last table here is the chi-square test or the Fisher's exact test, tells you the significance of the contingency table. So by doing this, you can evaluate if your PC or PC1 or PC2 is correlated with some categorical variable. So from the Pca result, we have confirmed that actually our samples are, our different groups are separated on PC1. And now the question is, this is metabolomics experiment. We want to know which metabolite have been detected. So this can be done by the feature table here. So in the feature table, every row is a potential metabolite we measured. So the most important columns are the first 5 columns. So we can look at them. The first column is the featured ID, and the second column is the retention time when the compound elutes out from our LC system. And the M over that, actually the mass of the compound. And the fourth column is annotation according to the mass. So still the annotation in untargeted metabolomics is the bottleneck for data interpretation. So it can, the simplest way to annotate a metabolite is to matching the mass we measured with the database. Of course, with some potential modifications or adducts already considered here. So for example, in this case, you can see the mass of the feature is 59 something, and this mass is the same with the acetic acid in the database. Of course, you can imagine that there are many different types of compounds may have exactly the same mass. So in this case, actually, we cannot distinguish them. That in this case, we will put semicolon here to separate different annotations. Of course, sometimes hundreds of compounds have exactly the same mass, so we only put top 3 here. And if you want to know more, you can click on a row. And more information about annotation will be shown in the annotation tab on the right. So when there are multiple compounds have exactly the same mass, it's very unlikely we can say this annotation is correct, confidently. So we need some other information. So another information we can use is to matching the spectrum we measured with the records in database. So you can see this is the 5th column annotation MS2. So when there is a plus sign, that means the spectrum in this feature is mapped to a record in database. Doesn't mean this is a good matching, but as long as one of the peak is matched, so there is a plus sign. For example, here for the feature 17, we look at alanine here. There is a matching. Actually, this peak is from the parent ion. It's not fragmented, so it might be not useful. But because we have MS2 matching or MS2 peak matching, there is a plus sign. As another example, we can select, for example, all the features with MS2 annotation by plus sign here. For example, maybe this one here, we can see is also a matching of the parent ion, or maybe this one. You can see there are two fragment peaks matched to the reference. You can see on top is the peaks we measured. On the bottom is the reference peak, reference spectrum for annotation. Yeah, if there are peaks have the same mass, not exactly the same mass, but the mass in the range of mass tolerance, it will be green. So you can see we have two peaks matched here. So there's a plus sign. Of course, in many cases, we have also good matching. Giving example, maybe this one, we always have good fragment of glutamic acid. So you can see there, most of the peaks are matched. Yeah, so it's a very good match here. In this case, we can say for sure this is the right annotation. Yeah, what we are seeing here for feature 82 is glutamic acid. And you may notice that for some of the annotation here, we have the letter STD and a score. So this is some special for our BioMS annotation. We have measured many pure compounds. We know how this compound elute, when it will elute from our LC system, how the compound will fragment in our MS. So most of the cases when we have STD, we have a higher chance to have a right annotation. And other than the MS1 and MS2, if we have STD, we can also compare the retention time, just because we know when the compound will come out from our LC columns. So this information is on the second column. The retention time, for example, in this case is 432. And for the notation, we know the retention time is 440, so it's very close. It's only 8 seconds in difference. I think if the difference is less than 30 seconds, it's a very good matching. Maybe less than like 50 seconds is also acceptable. But that's another information we can use for annotation or developing a confidence about the annotation. And also, one thing we need to check is the chromatogram. Sometimes we have a good chromatogram. For example, in this case, it's a very clean peak. The baseline is around 0, and we have a rather sharp and nice peak. But this is not always the case, right? We can check a few more. Yeah, this peak I think is also okay, but here you can see this peak is very wide, and we are not sure this is a pure compound. The peak here looks okay, but the identification for this peak is at the retention time 346. Yeah, so this might be not a pure compound. So you should also be careful with the peak shape here. Yeah. Okay, so that's how we can look at the feature table and how we can evaluate the annotation. And of course, we say the advantage of xcmsViewer is it's bridging the results of statistical analysis with the raw peaks. So actually, most of the cases you remember in this analysis, we have done the t-test to compare different groups. So if we want to visualize the t-test result, we can use the feature tab on the left. By default, this scatter plot shows have the retention time on x-axis and MR with that on the y-axis. But to show the t-test result, we can change it here. The x-axis we want to be t-test and the y-axis also t-test. And now we decide which t-test we want to show. Let's say we now want to check the before exercise and after exercise, right? And we will show the result as a volcano plot where the axis is the mean difference of two groups, or we also call it fold change. The y-axis is the log transformed p-value or log transformed FDR. Yeah. So the interesting compound will be on the top left and top right side. So this mean difference is always calculated using the before minus after. That means the ratio is before divided by after. That means on the right side, the metabolite is high in the before group. On the left, the metabolites are high in the after group. Yeah. So what we can do is to select, for example, the top right corner. And when we select the multiple metabolites, the anode will be disappeared. You have to further select one of the pawn here, and the node tab will show you the chromatogram and MS tube again. So to select one of them, we can look at the feature table because here we are selecting, I think, 9 different pawns. We can look at the feature table now. It shows us the 9 pawns we are selecting. And now we can further evaluate which compound we want to work with. Of course, if we have a standard compound, we want to check it because it's easy. We can have easy confirmation, and we have MS2. We may also want to check it. But sometimes we just don't know anything about a feature, right? Here you can see, yeah, for example, we even don't have a compound known have this mass, right? But it's also interesting because it's just on the top right corner here. Is it one of the 3 here? So because I think this compound is very interesting, right? So you can see, yeah, that's it. Yeah. And you can see also evaluate if you think this feature is interesting by looking at the feature general tab here. You can see it goes step up from after 24 hours to before. Yeah, so you can also show this as a box plot like plot. We call this B swarm, for example, group. Then you are splitting your 12 samples into 3 groups after 24 hours and before. And we can see the pattern of this metabolite is just goes up stepwise. Yeah. So this is very interesting. But unfortunately, we don't know what this compound is, right? So in this case, we can still do something. Because we find here, actually, we have a lot of MS2 spectra. So although we don't know which compound may generate this spectra, but what we can do is to infer the structure from the MS2 spectra or mass spectrum. So this can be done by tools like Sirius. We also have a link below the video. You can check the tool there. And to do so, you need to download the spectra. And then it stores the spectra in the MGF format, which is acceptable by most of the tools for structure inference. Yeah. So actually that's why. So we don't want to exclude those metabolites at beginning, those metabolites which are not annotated at beginning, because they may carry some very interesting biology. Yeah. Just that we don't know that doesn't mean it's not interesting. Yeah. But still, on the other hand, even there is an annotation on the MS1, or according to the mass, it doesn't mean it is a correct annotation. It's still very likely the correct annotation is not on the top ranked annotation here. So that's why we need to evaluate the annotation in so many different ways. So clearly this is a bottleneck in the untargeted experiment. So you can also play with some statistical analysis here in this feature general tab. You can compare different groups to see its p-value calculated from different tests like p-test or parametric test. You can also use different colors to show different groups. And actually this volcano plot is highly interactive. You can use different colors to show, for example, we can use anode MS2 here. There are two colors. The purple one the ones have MS2, and the green ones are the ones don't have MS2 matched to database. And we can also, if you want to know a feature, you can select, for example, feature something, and you can find them to see where are they, or you can find them in different columns. You can see glutamic acid, for example, or glutamine here. We can find where it is. So you can quickly find the metabolite you want to check in a targeted way. So this is the xcmsViewer interface. Let's have a quick summary at the end. So the xcmsViewer, in xcmsViewer, we have to do the calculation of t-tests like correlation analysis. Sorry, the correlation analysis have not been shown yet. I can quickly show you how to do that. To show the correlation, we can use, for example, the x-axis is the R and the y-axis maybe the log P. And what is interesting, of course, is on the top right corner here. We can see which feature it is. And of course, because we are correlating this metabolite intensity with the troponin 1, and maybe we can also use troponin 1 here. You can see this is a very nice correlation. Yeah. And the p-value, and you can see the R. Again, this is a fake data only for the purpose of demonstration. Yeah, so you can visualize your data in many different ways. Yeah. For example, you can use sample, and it's always auto. You can see the sample of after and the and after 24 hours, and you can see the x-axis is after and the y-axis after 24 hours. And we can use lasso selection to select those metabolite of the diagonal. Those compounds are high in the 24 hours, but low in the after. Right? So we can see what are they here. That's another way to select the interesting metabolite. Okay. So in xcmsViewer, all the results, most of the statistical results has been pre-calculated, and this result can be shown on the left panel. Yeah. We show them on the left panel because those statistical results are useful to prioritize some interesting features for us. Yeah, like the t-test we can show in the volcano plot, correlation analysis. Yeah. And then we can interactively select a subset of interesting metabolite or a subset of samples. And those selected samples and metabolite will be passed to the right panel. Some statistical analysis will be calculated based on the samples and metabolites you selected. And the result will be organized also in, for example, in the figures, in plots, or in tables. You can quickly check results and develop your hypothesis or try to confirm your hypothesis. Yeah, that's how the xcmsViewer is developed. And very importantly, when we work with untargeted metabolites, is we shouldn't trust an annotation blindly, or just to give the mass to somewhere and then do like enrichment analysis directly, just because there are so many different compounds may have the same mass. So we should think about if the quality of the annotation is good or not. So to check the annotation, we have different ways. The first thing is to check the chromatogram. The best metabolites will have a good shape of chromatogram. And also, of course, annotation according to mass is important. We can rule out 99% of other compounds, but still it's not very useful to say something for sure. And if we want for sure, we need to check the spectral matching. If it's a good spectral matching, then we can say rather for sure already, or at least we can say the metabolite that we are measuring have some structural similarity with the annotation. And because at BioMS we have standard compound or we have the reference compound, so when we have the metabolite annotated with STD, and it's also useful to check its retention time. So this is another resource we can use for our annotation. And the last thing is if a feature, we don't know what it is, but it generates some mass spectrum, and we can use this mass spectra to infer the structure. So this can be done by downloading the MGF and using some structure inference tool. Yeah, that's xcmsViewer. I hope you know better how to work with it. And thanks for watching.